Good morning, everybody. Today, let us see experiment number 7, which is based on optimal system operation. We are having two programs here, economic operation or optimal system operation for a system without losses and for a system with losses. We have two separate programs. We'll see one by one. First program, economic operation without losses. CLC. So this is going to clear the screen. Clear instruction will clear the variables n is equal to 2. So again, here again, it is a straightforward programming approach where we do it for a particular program. We are not taking any, we are not prompting any input here. It's not written in general. Of course, that approach also can be followed. Just to illustrate how we can do it directly, it is been done. N is equal to 2. Total number of plants in the given system are 2. PD is equal to 245. In the given system, the demand happens to be 245 megawatts. So PD is taken as 245. AI and BI are the coefficients of cost equation. So AI is having A1 and A2 as 0.2 and 0.25. BI as B1 and B2 40 and 30. Initial value of lambda is assumed to be 41. So lambda is equal to 41. Then lambda PREV is equal to lambda. So we are going to initialize the value of lambda and it will be taken as previous lambda. EPS is equal to 0.005, which is the error value or tolerance value. Acceptable tolerance value is 0.005. Delta lambda is equal to 0.01, which is nothing but the difference between the expected as well as actual lambda. Pg max is equal to 125, 125. That is for both the plants P1 and P2. Sorry, for both the plants 1 and 2, maximum power is 125 and 125. Pg minimum is 2020 for both plants 1 and 2. Minimum power that can be generated are 20 and 20 megawatt respectively. Now we are going to initialize a variable Pg, which is equal to 100 into ones of n comma 1. Ones of n comma 1 means it is a matrix that contains n rows and one column having all the elements being 1 multiplied by 100. So finally Pg will be a matrix containing n rows and one column having all the elements being 100. Then di is given as 120 and 100, which is another coefficient of cost equation. For plant 1 it is 120, for plant 2 it is 100. Then iteration is carried out here. So the initialization of the iteration is done, which is nothing but m is equal to 0. M defines the iteration count. So far we have just accepted the input. We have just declared the input of the given date for the given problem. Now starts the loop. While absolute of sum of Pg minus Pd is greater than EPS, it is checking for the power balance condition here. You very well know that Pg is equal to Pd plus losses. Total generation is equal to total demand plus losses. That is nothing but your power balance equation. Since here losses are not there in this part of the program, Pg will be equal to Pd. So Pg is equal to Pd means Pg minus Pd will be equal to 0. But instead of 0, they take up the tolerance value and they say Pg minus Pd, if it is greater than 0.005, then for I varying from 1 to n is nothing but your total number of plants. Here it is 2, so I varies from 1 to 2. Pg of I is equal to lambda minus Bi of I divided by AI of I. Already you have seen this formula, lambda minus Bi by AI for Pg. If Pgi, whatever is obtained, is greater than maximum value, set it equal to maximum. If it is less than minimum, set it equal to minimum. This is what we do it in case 2, as you know. Then once this is done, we are going to compute the cost. C of I is equal to A of I AI of I by 2 plus Pgi square plus Bi Pgi plus Di. This is nothing but your cost equation, which is Ci is equal to half AI Pgi square plus Bi Pgi plus Di. And then the other possibility is if sum of Pg minus Pd is less than 0, that means if it is a negative value, then lambda previous is equal to lambda, and lambda equal to lambda plus delta lambda. That means if your power balance condition is not satisfied, you'll have to go to the next iteration. You'll have to execute the iteration by updating the value of lambda, and that value of lambda will be previous lambda plus this delta lambda. So again here, if it is a negative value, you'll be adding delta lambda. If it is a positive value, you'll be subtracting delta lambda. So if sum of pg minus pd is less than 0, then in the second line you are having lambda plus delta lambda, and if sum of pg minus pd is greater than 0, it will be lambda minus delta lambda. Now if m is equal to 10,000, break. That means if you don't get a solution up to 10,000 iterations, stop the iterations, and then otherwise go for m is equal to m plus 1. In every stage m will be updated, that is iteration will be updated. After first iteration, go for second, then third, fourth, so on, and let it be executed until m becomes 10,000. So maximum 10,000 iterations we are allowing. End. Then for I varying from 1 to n, again cost will be calculated. Then display the final value of lambda, display the final value of pg, sum of pg, total number of iterations, and then finally total cost. Next we'll go to economic operation with losses. Now again, as usual, CLC instruction, clear instruction, again taken for a particular case. N is equal to 2, two plants are there. PD here is different for this problem. Demand happens to be 237.04 megawatt. A and BI are defined, A1, A2, B1, B2 from the problem coefficients of cost equation. Initialized or assumed value of lambda is 20. Lambda previous is equal to lambda. It is declared. EPS is equal to 1. Here the tolerance value is taken as 1. Delta lambda is taken as 0.25. See, here comes the difference. Theoretically, we have a formula for calculating delta lambda. Here delta lambda is taken straight away. PG max is defined 200 200. PG minimum is defined as 0 0 as per the given data. PG is equal to zeros of n comma 1 as usual. It contains n rows and 1 column having all the elements as zeros initially. PL represents transmission loss. PL is 0. M iteration count is 0. Capital B represents the B coefficient matrix, which is zeros of n comma n. It is of the size n cross n having all elements zeros. Then BCEF is another variable used for the B coefficients that are given in the problem. So 0.001 0. In the second row you are having 0 0. That means since its two plants are there in the system, B11, B12, B21, B22 are there. And again now we are also calling for another coefficient of cost equation, which is DI, which is 12 and 16, D1 and D2. While absolute of sum of PG minus PD minus PL is greater than EPS. If you just compare with the previous program, here we have PG minus PD minus PL greater than EPS. That is, loss is also taken into account. Earlier we just had PG minus PD greater than EPS. For I varying from 1 to n, here again, as I told you, the approach is going to be different from that of what is done theoretically in the class, in the subject. Here we are going to define capital B, one variable. There is a formula for that capital B that is dropped here, and there is another formula for small b, another variable. So PG will be equal to capital B by small b. Anyway, this also will be discussed in the class later on. PL is PG transpose into B coefficient into PG. PG is a matrix, B coefficient is another matrix. So PG transpose into B coefficient into PG will give you transmission loss. This already has been done in the class. If PGI is greater than PGI max, PGI will be set it equal to maximum. If PGI is less than PGI minimum, set it equal to minimum. And finally calculate the cost, and then calculate the final transmission loss, and again recalculate the cost, and then coming to the lambda value, that is whether to continue or not the iteration. If Pg minus PD minus PL is less than 0, then add delta lambda to the existing value of lambda and go for the next iteration. If lambda previous, else if it's a positive value, subtract the delta lambda from the actual value of lambda and continue the iteration. M is equal to m plus 1. Again here also until 10,000 you will continue the iterations. Finally display the value of m, total iterations undergone, lambda previous, Pg, transmission loss PL, and x the total generation which is P1 plus P2, C the total cost of generation. So this finishes the program on optimal system operation or economic operation for a system with losses. So this finishes experiment number 7.